In this lesson, lesson 21, we're going to once again compare linear and exponential functions. We're going to compare their equations, their graphs. I have a graphic organizer for you that we can use, and we're going to start filling it out. I have two graphs here. The green one is the exponential, and the red one is the linear model. There are two separate functions. I just happen to graph them in the same graph. Now, you notice that my exponential graph here has that line, that little tail that is going on almost the x-axis, but it's not quite touching it. That is what we call asymptote. So if at any time you forget what an asymptote is, you can Google it. Now we see a definition of a line that continually approaches a given curve but does not actually meet it. Asymptotes are definitely a characteristic of an exponential graph. But let's go ahead and get started with the comparison. I want to know how these are the same or different. We're going to start with our equation, or general form, whatever you want to call it. In a linear model, we have the equation y equals mx plus b. I'm going to use function notation. So it's f of x equals mx plus b. And because I want to use the same variables, I'm going to use a instead of m. So it'll be f of x ax plus b. My exponential function will be f of x equals ab to the power of x. What are the meanings of a? In a linear model, a means the slope of the line, rise over run, and b stands for the y-intercept. In an exponential model, a stands for the initial value. So when x equals 0. B, on the other hand, stands for the common ratio. If you're multiplying, if you're dividing, we usually call that the common quotient. Let's work with an example. I have a linear function. We're going to use that for our examples that follow. F of x equals 2x plus 3. And I'm also going to have an exponential model that we can use for the examples. F of x equals 3 times 2 to the power of x. And these are the actual graphs that you see on the right-hand side of the screen. What I'm going to attempt to do in this lesson is deconstruct the function notation in a way that you will understand what the problem is asking you to do. So we have to figure out a rule for finding f of x plus 1. So there's a couple different ways we can go about this, and the way that I like the best is by using numbers. So I'm starting with 0, 1, 2, filling out a table based on my linear example, 2x plus 3. And I simply plugged in the x values, and that's how I arrived to the values for the y, or f of x, column. Now, what if I needed to find f of x plus 1? Well, what exactly does that mean? Well, that means that I'm adding 1 to the value of x. So if the value of x, let's say, is 1, then what I'm doing is adding 1 to 1. So if x is 1, then my new value of x plus 1 would be 2. And when I look at the table, f of 2 is 7. I'm going to fill out a table so you can see this more clearly. If x is 0, 0 plus 1 will give us f of 1. And we know that f of 1 from our table is 5. So I could just go ahead and delete all this math, and you will know where I got that from. Well, let's say I wanted to do that for x equals 1. If I do that for x equals 1, then f of x plus 1 will be 2. And so if you notice the pattern here, our table of f of x plus 1 started at 5 and then it's going to continue to increase by 2. And the reason it does that is because our rate of change is a plus 2. So we can say that in order to find f of x plus 1, we just have to apply that rate of change. So we can just add 2 to whatever f of x is. Now, how would this work for an exponential model? In a linear model, your slope is going to be arithmetic, right? So it's going to change either by adding or subtracting. But in an exponential model, your rate of change is going to be geometric in nature, so it's going to either change by multiplication or division. Let's fill out a table to see our initial values. I'm going to use the same x, 0, 1, and 2. For this initial column of f of x, all I'm doing is substituting the value of x for your exponent, reminding you that the equation here is 3 times 2 to the power of x. If I look at what the common ratio here is, my common ratio here is 2. So that means that I'm multiplying the y values by 2. So when x is 0 and y is 3, in order to get the next value, I'm going to multiply that 3 by 2. And that is our common ratio. So if I'm using that knowledge to fill out the values for f of x plus 1, then I just add 1 to that x. So f of x 0 would be f of x 1. F of x of 1 would be f of x 1 plus 1, which is 2, and so on. And basically what we're doing is applying that common ratio of multiplying times 2. So we can say that that is the rule. To find f of x plus 1, or the next value that comes, we multiply by the common ratio. And then the last difference that they have between these two models is the type of situations that you would use them. So I'm going to give you an example of a story problem here. Charles had $3 in his bank account and earns $2 of allowance every week, so he's going to add $2 every week. That type of growth is a linear growth, whereas if you gain any sort of interest, then of course we would be talking about an exponential growth. Also, when we talk about population, there's 3 goldfish and the population doubles every month. That's a typical exponential example as well. So I have this other table below that I want you to try to work out on your own. If you have any questions about it, please bring it to class. We want to find out f of x plus 1 and subtract f of x from that answer.